In our previous session of equilibrium of rigid body or static equilibrium of rigid body, we have seen very few problems as well as what are the different types of joint, and basically we have focused that how we make the free body diagram of a rigid body subjected to number of forces as well as the moments. In this session we will try some examples of a rigid body when it is subjected to number of forces. Here we will see that how we make the free body diagram. If the rigid body is not made by a single bar or body, it is a combination of body with joint of fixed joint, pin joint or roller joint, then how we make the number of free body diagram and then get the unknowns. So I'll start with the first problem. Suppose I am having a single bar AB. The B joint is a pin joint. Now first read the statement that find the normal reaction at point A and B. The mass of the bar AB is 200 Newton and length is 6 meter. So basically the total length is given. This is an intermediate point. Let this is point C. We are having a point force acting at point C and making an angle 30 degrees from the horizontal, not from the bar. The angle of this point force is 30 from the horizontal direction. Now the point A doesn't show any kind of joint, that means it is just a point contact. And when we know that if we have a point contact, then the reaction will always be normal to the surface of the contact. That means suppose the bar A is here and this is the wall, so the reaction will be perpendicular to the wall. On the other hand, if the wall would have been some angle, suppose the wall had an like this is my wall, so the normal reaction will be perpendicular to the wall. It doesn't have any relation with the bar. Sometimes what students do, they put a reaction normal to the bar. No, this is not correct. The reaction will always be normal to the surface. So let's make the free body diagram of our bar. Here is the free body diagram of the bar. You see here that we had joint B, which is a pin joint, and we know that when we remove the pin joint we put two forces. In my case I don't know the value of any of the forces. I am taking these two directions randomly. Similarly, I am having a reaction at point A. There will be only one reaction because there is no joint. If there is nothing, it's just a contact, that means the reaction will be perpendicular to the wall. And this is my point C, which is already having a force of 100 Newton. Since I know that the length is 6 meter, this will be the 1/3 of the length, that will be 2, and remaining will be the 6 minus 2, that will be the 4. As I have completed my free body diagram, my next job is to write the equation for the equilibrium. That means I have to balance the forces as well as the moment. Let's balance the horizontal forces. When I will balance the horizontal forces, there are one horizontal forces NBX, one horizontal forces NA, and next horizontal forces will be component of this load, which is 100. So horizontal force reaction of this will be 100 cos 30, and the vertical reaction of this force will be basically 100. So these are the two component of this force, cos 30. Now I am having NA, which is horizontally and rightward. Suppose the rightward direction is positive direction and upward direction is positive in my convention. So NA plus 100 cos 30 minus NBX. When I will balance the vertical forces, there are four vertical forces. One of this force, only three, sorry. One is the gravitational force, which is the weight of the bar, which is acting from the center of the bar. So this position of this point, which is the CG centroid, is 3 meter away from this end as well as 3 meter away from this end, because the total length is 6 meter. So when I will write the vertical force balance, I am having 100 sine 30, which is upward, 200 which is downward, as well as the NBY. here I have one unknown, two unknown, three unknown, so these two equations are not sufficient to get three unknowns. So let's write the equation for the moment. I can take the moment at any point, maybe at A or C or at the centroid or B or anywhere on the body. If the rigid body is in equilibrium, the moment should be balanced at all the points. But I am going to take the moment at point B because I know that these are the two unknowns. So if I will take the moment at point B, the effect of these two unknowns will gone because the distance of this point with these forces is 0. If I would have taken a reaction at here, again I will be having three unknown in my equation, and my equation, when I will get the equation, it will be more complicated to solve. So always take the moment at a point so that you can remove maximum unknown. If I will take the moment at point B, there are number of forces, one is 200, and as I don't know the normal distance of point 100, the simple way is to make the component of point this force, so that I will be knowing the vertical and horizontal distance, which are easy to calculate. As I know, this is the 30-degree angle. So when I will balance the force at moment at point B, one of the force will be NA, and the line of action of NA is this, so perpendicular distance will be 6 sine 30. The second force is 200. It is passed at the center, so this is 3, so this will be half of this distance, so 3 cos 30. Next force will be this vertical force and this horizontal force. So vertical force is acting at this point, which is 2, so this distance will be 4 cos, this is basically 4, so it is 4 cos 30, and this is 4 sin 30. When I will write all the forces with the distance multiplied with the distance, I am having this equation, and as I know that 200 force is acting in the downward direction, so its effect will be counterclockwise, and effect of this 100 will be clockwise, 100 cos 30, 100 sin 30 will be clockwise, as well as effect of NA will also be clockwise. If you will see my previous video where I have explained that how to find the sense of this moment. So finally I will be having this equation. When I will solve this equation, I will get the reaction at this point will be 57.73 Newton. Now let's see the next problem. In my next problem, I have extended this problem which we have already solved. Only the thing what we did, that instead of having this force, I am having a pulley system where there is a force mass m is suspended from this pulley. If you will see the figure in a bigger way, this is my diagram where I am having the same bar which we have seen in the previous case. The point A is just a contact, point B is a pin joint. This is my force. In my previous case this was given as 100, but here I am having, there are pulley 1, pulley 2 and pulley 3, and there is a force acting at M, so where there will be a force mg, and these are the two tension, and the tension will be basically mg by 2. The same tension will be transmitted here, so here also the T, this is mg by 2, and the same tension will come here, this will be again mg by 2. So now my problem will become same, and this is the condition here. Again I am having the same problem, and my T is nothing but the mg by 4. So now when again I will write the equation of all the forces, I'll get a value of NA here, and here NA is coming out minus 23.09. As mass M is given 100, the weight of mass means this direct mg is given 100 Newton, and the weight of the bar is 30 Newton. In my previous case the weight was 200 Newton and the force was 100, but here the forces and the weight are different, so I am getting an answer that is minus 23.9. We have to solve the same procedure which we have seen in the previous case, but answer is coming negative. That means the reaction at point A will be negative, means there will not be any contact. The bar is about to, the bar is not applying any force on the wall. Now let's see the next problem. This is my next problem. Here I am having two bar AB and BC connected at point B. All the joints are pin joint and a cylinder. This is a two-dimensional view of weight W and diameter 2 meter. So statement says that AB and AC are two rigid rods connected at B by a pin joint. Agree. The two rods support a cylinder of weight 15 kilonewton. So the weight of this cylindrical body is 15 kilonewton. Find reactions at point B. Now what would be the reaction at point B? If we will see directly this problem, actually B point is connected to this, so there will not be any force if I will not split these two rods AB and BC. So let's start the problem. First job, whenever we are having a equilibrium problem of rigid body, the first job is to make the free body diagram. Here also we have to see that how many free body diagrams we can make. The first free body diagram of the removing of these two joints only. I am having the cylinder here, the weight of the cylinder is acting in the downward direction, and I have removed the two pin joints, so two forces. Suppose these are my reactions, suppose this is Cx and Cy, and this is Ax and this is Ay. The second free body diagram would be only two bars. I have removed the cylinder also. So when I will remove the cylinder, there will be force because of the cylinder on the bar. This is R1 and R2, and this will be normal to the V bar. This is my point B. The next free body diagram can be just one bar. This is my bar AB. So this is my force Ax, Ay. This is my reaction because of the cylinder. Suppose this is R1, and I am having two forces. This is my Bx and By. Please understand, when you remove a joint, since this is a pin joint and you are removing these two bars separately, there will be a force at point B of rod AB because of this rod, and the equal and opposite force will act by this rod on this will be act by AB to rod BC. So if I will make the fourth free body diagram of again the point BC, this will be a reaction R1, R2, two forces Cx and Cy. Now I know that the B point is same for rod AB and BC, but I am separating out the B point. So I should take care that if I have considered the direction of forces for the first rod as Bx left rightward and By upward, there will be equal and opposite forces. Okay? Bx, and this would be my By. So please understand that if I am having the same point, or I am having a point which lie on the two rigid bodies, and I am making separate free body diagram, I should always take care that if I am assuming direction of reaction on first point, the equal and opposite reaction will come on the other point. So there are one more free body diagram of just a cylinder. This is my cylinder, and as I have seen here that the cylinder is acting a force on the bar, the equal and opposite force will be act on the cylinder. So this would be my R1 and R2, and there will be a force W which is acting in the downward direction. But I have to calculate this theta value, which is easy to calculate using the geometry. So now let's make the free body diagram. Here are my four free body diagram. I have considered these four free body diagram. This is the first free body diagram, in this case I have just removed the two joints. So now I have assumed the direction as shown in the figure. This is my second free body diagram, where I have made the free body diagram of cylinder. So these are the two reaction R1 and R2 coming because of the rod AB. This force is basically act because of the rod AB. So equal and opposite force I have made here. This force act because of the rod BC. So equal and opposite force I have made here. Now the third free body diagram of AB. So these are the two forces, and I have taken these forces randomly because first time I am considering point B, but I know that when I will make the counterpoint of B, I have to take the reaction equal and opposite to this point. So these are my four free body diagrams. Now let's write the equation for these four free body diagram, because we know that once we have the free body diagram, the next job is to write the equation for force balance as well as the moment balance. So I have to write the equation for this free body diagram as well as for the other free body diagram to find the unknowns. Here are my four, this is the first free body diagram, and for the first free body diagram here are my equations. As I am going to balance the horizontal and vertical forces, if I will balance the vertical forces, these two forces will be balanced by W. If I will balance the horizontal forces, only two horizontal forces which I have considered equal and opposite, because AX is taking rightward and this is leftward. So when I will balance it, these two forces will be equal and opposite. Now the next is to take the moment. I have freedom to take moment anywhere, here, 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 here. If I will take the moment here, there will be 4 unknown in my equation. So the easy job is to always consider a point where you can remove as many as unknowns. So I am going to take the moment at point A. So when I will take the moment at point A here, the effect of AX will gone, AY will gone, as I know that the line of action of CX is also passing from point A. So CX will be again having a zero moment at this point. So now I have only two forces, one is the CY and one is the W, and I know from the equation that this distance is 4 and this distance is 2. So when I will write the equation of moment, I am having CY into 4 and W, the line of action of W is passing here. So this distance is 2, so W into 2. And if I'll see the direction, W is acting in the downward direction, so its effect will be clockwise. CY is acting in the upward direction, so its effect will be counterclockwise. So now I am having my equation. I am assuming clockwise positive and counterclockwise negative. The total summation of the moment will be 0, and which will give me the value of CY. This is the equation for the vertical forces and this is the equation for the horizontal forces. So from these three equations I will be able to calculate that my CY will be 7.5. When I will put this CY into this equation, I will get my AY is again 7.5, and when I will solve this third equation, I will be able to know that the relation between AX and CX, but I am not able to get the amount or the amplitude of these two forces, so I have to move to the second free body diagram. Now this is my second free body diagram of the cylinder. When I will write the equation for this free body diagram, I know that, suppose these are my two references axes, so I have to balance the horizontal forces. In my horizontal forces, the horizontal component of R1 and R2 will come into the picture. When I will balance the vertical forces, the vertical component of these two forces will be balanced by W. So first I have to calculate the angle theta. Here if I will see, I know that this will be 90 degree and this is 1, this is 1.25 given, so using these two values I will be able to calculate the value, and my phi is coming, my theta angle is coming 51.34 degree. This is basically my theta angle here, and symmetry I know that this is also be theta. These two angles are theta from the vertical, and when I will write the equation for the horizontal force balance, I will be able to know that these two reactions will be equal. From the symmetry I know from the intuition that these two reactions will be same, but if I will balance the horizontal force, it will be proven that these two reactions will be equal. Now when I will balance the vertical forces will give me the value of R1, which is coming out 12 kilonewton, because the force W in the downward direction will be balanced by the summation of the vertical component of these two reactions, and these two reactions are equal. So my equation will be 2R1 cos theta. This vertical component will be cos and the horizontal component will be sine. It is not conventionally that horizontal and vertical component will be sine cos. I know that if I know the theta of this side, the component of this side will be defined by the cos and the component of this side will be defined by sine. So from this I am getting the R1 will be 12. Now again I will make the third and fourth free body diagram, but I have to only use one free body diagram, either this one or that one, because now I know the R1 value, I know the AY value, but I don't know the AX value as well as BX and BY value. So let's take the third free body diagram. When I will balance, I will write the equation. Again the question arises, at which point we have to take the moment, maybe at B, here or here, but I know that if I will take the moment at point B, the effect of these two unknown will go away and I will be able to calculate the third unknown, that is AX. So when I will take the moment at point B, R1, that is in itself in perpendicular side, so R1 will be 1.25 and this is acting in this side, so its effect will be counterclockwise. AX is acting in this direction, so its perpendicular distance will be 2.5, which is given initially, and the AY is acting in the upward side, so distance is given as 2. The effect of AY will be clockwise, AX will be clockwise, but R1, effect of R1 will be counterclockwise. So my equation will be AX into 2.5, AY into 2 and R1 into 1.25, which will give me a value AX is equal to 0. As I know that AX is equal to 0, I know that from the first free body diagram that the AX is equal to CX. So my CX is also 0. Now when I will balance the forces, I know that this is 90 degree, and when I will balance the, and this angle is theta, so this is 90 minus theta. So now if I will balance the horizontal and vertical forces, I know that the imbalance of horizontal forces, there will be three horizontal forces, Bx, R1 cos 90 minus theta and Ax. And as Ax is 0, when I will balance the horizontal and vertical forces, I am getting that my By is 0 and Bx is 9.37, but the negative sign. So this negative sign indicates that I was considering the third free body diagram and my Bx is coming minus 9.37. That means the direction of this force will be rightward instead of leftward. So in actual system, this rod is applying a force to this rod in this direction, and this rod is applying a force into this in this direction. But initially I have considered the force towards the left side, which is coming up. Actually I have said wrongly that this rod is acting a force in this direction this way, because these two rods are just pulling each other. So rod 1 is applying a force on rod 2 towards left, and rod 2 is applying a force on rod 1 towards right, because both the rods are pulling to each other so that they will not move apart and they will bear the weight of the cylinder. So finally I know that the actual direction of the force Bx will be right and By will be upward. Thank you.